Hi everyone. So this is lecture 10, which is a review of matrix algebra. So today we're going to start out, I'm going to give a little perspective. This is sort of a change lecture. It's an in-between two different sections. Then we're going to talk about linear systems and what they are and how to set them up. Then we'll review some index notation, which is maybe something that you haven't emphasized before, which will matter for us on computing. And then we're going to talk about the Gauss Elimination algorithm, and we're going to do that by hand in preparation to code it in our next lecture. Okay, so let me just go ahead here and talk about a little bit of perspective. So up until now, we've been learning about numerical computing. We've programmed, we've done things like this. And we're now going to switch our lectures from just focusing on computing itself to focusing on the actual solving math problems with these tools that we've learned. So some of you who have been following along and doing the videos or taking the class may feel like you're struggling to still understand and learn these numerical computing concepts. And I want you to sort of rest assured that we're not going to introduce new ones. So at this point, we sort of learned the program that we're going to learn, and from here on out, we're going to be doing math problems using those computing tools. So if you're someone that feels like this has been an inundation and it's going really fast, it's okay. We're going to continue to use those things. So work on honing those skills, but we're going to get better at them over time as we do them. Now, there are perhaps some of you who are on the other end of the spectrum and feel like you've got numerical or you have computing tools down. This has been a review for you. And for you, I'd say, great, you have a great foundation, and recognize that here we're taking a turning point, and we're going to learn some new things. And so if you've kind of been on autopilot, now's the time to kick it in gear and realize that some of this stuff might be new to you. All right? So that's all I'm going to say about this perspective. So I'll just maybe put down here, this is a turning point. Okay? And in this turning point, we're going from numerical computing to solving math problems. Okay, so maybe this would be better like that. All right, so this is really a turning point. All right, so let's go ahead and do that. Let's turn. Let's turn and think about linear systems. So a linear system of algebraic equations looks something like this. Okay, this is just an example. So I have 3x0 minus x1 plus x2 is equal to minus 3. And then I have minus x0 plus 2x1 minus x2, and that's equal to 8. Let me scroll a little bit down here so I don't have to hurt my hand so much writing at the bottom of my tablet. x0 plus, minus, let me get to my minus, this is just my example again, minus x1 minus x2 is equal to 1. All right, so this is an example of a system of linear equations. And so what do we notice in linear algebra? We notice that there are no powers. Okay, so we talked about this at the beginning of class. There's no x1 squared in here. Okay, there are no products. Okay, so I don't have x1 times x2, for instance. Okay, so that's how also I know it's linear. And there's no differentials. Okay, so I don't have dx1, dx2. Okay, something like this. So this system is linear and algebraic. Okay, certainly in math class, an analytical math class, you're going to talk about something more formal than this. You might learn the formal definition of a linear system, and then you'd have to go through and show that this is linear. This is sort of the shorthand. Okay, this is, the short way. Okay, not really rigorous, right? This is, or formal. Okay, by formal I mean has the form of, right? So But this is just an easy way to look and see if the system's a linear system or not. Okay? So that's a specific example that we can tell. What about a general case? What does the general case look like? So let me write down the general case down here. So let me get our screen a little bit more. So here I might have a0, 0, x0 plus a0, 1, x1 plus, and then I could have lots of terms, plus a0 n minus 1 x n minus 1 is equal to b0. That would be one equation. Then the next one I would have is a1, 0, x0 plus a1, comma 1, x1 plus many terms plus a1, comma n minus 1 x n minus 1 is equal to b1. Okay, could have many equations like that all the way down to a n minus 1 0 x0 plus a n minus 1 1 x1 plus many terms plus a n minus 1 a n minus 1 x n minus 1 is equal to b n minus 1. All right, so let me point out just a couple things about this, right? So this system is an n by n system, okay? So why is it n by n, but I go from 0 to n minus 1? Well, I'm counting like programmers count, okay? So I'm going 0 to n minus 1, but there's n of those, so this is an n by n system, okay? This is a square system, so that means I have n equations, okay, and n unknowns. All right, so that if certain properties hold in a square system, I can have a unique solution. All right, so again, in your math class, you will learn, and probably exhaustively so if you take a linear algebra class, all the properties that you need to make sure that this is a solvable system with just a single unique solution. And you'll learn about what happens if what that means when it is a unique solution, right? So they have like these solvability theorems, and there's all sorts of stuff known about linear systems about that. Okay, so that's really important in that class, and that's an important thing to know. In this class, we're going to kind of take it for granted, all right, that that I have a system here that's solvable. All right, so here I have this general or a general case. You can see these a's here. They're the coefficients, right? So they're the coefficients that sit in front. So these a's here, these are coefficients, right? Each of these are the equations, all right? And then these x's here, they are the variables, okay? And then over here, for lack of a better term, this is also part of the equation. I call this the right-hand side, okay? I'll use RHS for right-hand side. It's convenient to write down, all right? So we can write down an equation like this in matrix notation. So it's convenient to be able to write this down in that notation. So let's translate this equation to matrix notation. All right, so in matrix notation, recall I have A times X equals B. Now, what I have here, right, A, this is the matrix. X and B, these are both vectors. All right, and for me, I put 2 lines underneath a matrix, so that tells me it's 2-dimensional, and I put 1 line underneath a vector. Maybe in your class in math, you've done something like this, or something like this, all right, for a vector, and then I don't know what you do for matrix, okay? Usually in a book, they'll have big, bold letters for the matrix, all right? But I'm not going to do that. This is what I do by hand. I think it's convenient. I'm also going to represent this product between A and X as a dot product. All right, we talked about that in a video a couple days ago, and we're going to see it again today. I think it's useful to see that, to write it that way, right? So how do we translate this equation up here into matrix equations, right? Well, how do I go about doing that? Well, I can write down the A matrix right here, and I'm going to write it also using this index notation we'll talk about in the next section. I'll call that Aij, and I'm going to give it my braces, and the way that's going to go is A0, 0, A0, comma 1, A0, comma n minus 1, A1, comma 0, A1, comma 1, A1, comma n minus 1, many lines here, an minus 1, 0, an minus 1, 1, an minus 1, n minus 1. All right, so each of these terms here corresponds to these coefficients that were up there. All right, and notice they go in the same order if I write it in the order with these variables. So I've got A0, 0 here, A0, 1 here, A0, n minus 1 there, okay? So each one of these rows, each row is like an equation, okay? And each one of these columns here, okay, these are going to correspond to the different variables that it's going to be in front of, all right? And so that's how, when I'm going to now write down the x vector will look like x0, x1, down to xn minus 1, and that right-hand side vector b is going to go b0, b1, down to bn minus 1 as well. Okay? So, and I'm going to write this x, also we'll see in a second, as x, let's see, I write it as xj. I'm going to write b here as bi. All right? And what I'm going to see is I can also rewrite this product. So if you'll follow me over here, I can write a dot x equals b. I can, just one line under b. I can rewrite that as the sum over j of aij xj is equal to bi. Right? So that's going to be this index notation that I'm going to talk about in a second. All right? So, so this is how I translate, this general case into this case here. All right. So now I want to do a quick example. I want to do a little practice. Oop, forgot the E on practice. Okay, we're talking about practice for those of you basketball fans. Okay, so we're going to write the 3 by 3 matrix, okay, from above as A, X, and B. All right, so I want you to write A, X, and B of this 3 by 3 matrix. So I'm going to scroll up here, all right, so you can look at it right there. That one right there. I'll put a little box around it. Take that green guy right there. All right, so I want you to pause the video for a second, and I want you to write that out as A, X, and B. All right, so hopefully you paused the video and you did that. Let's do this on the video right here. Let's do it ourselves. Let's write down what it is. So I'm going to have A, open bracket, okay? And I said that each of these terms in front, the coefficients were the A matrix. So this is 3 minus 1, 1 on the first one. So 3 minus 1, 1. The next one is minus 1, 2, minus 1. Minus 1, 2, minus 1. And the last one is 1, minus 1, minus 1. 1, minus 1, minus 1. All right, x should be same as before, x0, x1, x2. We just have to use our general case here. And b, all right, this is the ones on the right side, and that's minus 3, 8, and 1. So that's b over here. B is minus 3, 8, 1. All right, so hopefully you got that right. If you didn't, pause the video and go back and look at what you did wrong and check it and make sure you get it right. All right, so that's it for part 1. That's it for the review of a linear system. Okay, number 2, index notation. All right, so when you're using arrays and matrices by hand, it's convenient to use what I call vector notation. So by hand, you often use vector notation. Right? And that's this notation, a dot x equals b. Right? Or maybe if you're doing, you know, 2 matrices, you have a dot b equals c. You know, so this would be our current linear system. This would just be the product of 2 matrices. Right? In your math book, you might see this as a, you know, bold, b big and bold equals c big and bold. Something like this. All right? You know, that would be your math book. Okay? But on a computer, all right, it's more convenient to think about things using index notation. All right? And why is it going to be that? Well, loops. Okay? In a loop, we had a counter. All right? We had an index that took us through that loop. And so it's really convenient to rewrite these thinking about what our counter is going to be. All right? And so let me write down the index notation for a couple common operations. All right? And then I'll back out the sort of general principles. So I'm going to do the examples first, and then I'll do the general principles. So here's some examples of index notation. Right? And you've probably used this before in your math class, but maybe you haven't thought about this in a separate way. Okay, so let's take a vector norm. Okay, so in a vector norm, I would have a vector v. I'm taking the norm of it. Right, and remember the norm is just like the distance formula. So I'm going to have the sum over I, v sub I squared. Right? So the index notation is really like telling you what to do with that vector norm. So the vector norm, you know, or the vector notation. So the vector notation, right, is the shorthand. It's really easy when you're writing it by hand, but writing it out in that index notation is harder, right? So now what does this one mean? You remember this means that, you know, I would have like v0 squared plus v1 squared plus, you know, all the way to vn minus 1 squared, right? I'm adding all those up, and then I take the square root of all of them. Okay? So the index notation is shorter than writing it all out, right? I have this I, okay, and I'm going to plug in I from 0, you know, I might even write out I equals 0 to n minus 1, all right? But I don't necessarily need to write out that 0 to n minus 1. I can just sort of know in my head that this is going to represent 0 to n minus 1, however long that vector is. All right? So there's the vector norm. Here's the dot product. Okay, the dot product is v dot w here. All right, so what is that in index notation? See if you can pause the video for a second, see if you can guess what it's going to be. All right, so what it is I'm going to have the sum over I of vi times wi. Right? Because remember what that is. The dot product, I take the product of the two, I sum them up. All right? That's the dot product. So that's going to be, you know, v0, w0 plus v1, w1 plus etc. etc. All right? You get that. All right. Let's the next one. Let's do a matrix vector product. Right? So in this case, now the matrix vector product, I'm going to have a dot x. So what is that going to be? All right. Well, I'm going to have another sum, okay, of a I j multiplied by x j, sum over the j. Right? Maybe that one is a little hard to stare at, but remember what you're doing when you do this product, right? You have this one, that one, times that one, that one, that one. So you do that times that times that times that. Right? Remember doing this in your math class. All right. So what you're doing is remember that the first one here is the rows, right, and J is the columns. So you're going down or going over the columns in the J, and you're going down the rows in X, and you're multiplying those and summing them up. All right. So that's the index notation for that one, right? And at the end, these guys you end up with just a single number, right? The vector norm, a norm is just a scalar. A dot product is just a scalar. But the matrix vector product is going to give you out some new vector, say yi. Okay, so that would be a dot x is equal to, y underline, all right, in vector notation. So here I have yi. I'm going to get something out that, in the end has 3 points, where the first one, that one came from that sum, and then I've got the other two that come from the other rows that I go through here. All right, the last one I'm going to write down will be the matrix product. Okay, and now I have A dot B. So this is going to be the sum over J of Aij, Bj, K. All right, and so again, this is very similar to the matrix vector product up here, but now I have, A looks like this, right, with another 2 rows, down here, and B looks like this, and I'm going to do the product, this way with these other columns. I'm going to do this one times that one. So I do the columns of this one multiplied by the rows of that one, okay, because I go down the rows here, go across the columns there. All right, and in the end I'm going to get out something that's like CIK. I'm going to get a whole new matrix, right, where that first one there, right, comes from this one, and then I'm going to go on and have other things in that C matrix. Okay, so what are the sort of general principles of this index notation? So what are principles? I'm going to rewrite that word. Principles of index notation. All right, so let's think about what we had here. So note that we've got one index, all right, for every dimension. So one index, one dimension. All right, when we do a dot product, okay, that's going to give us a sum over a repeated index. Okay, so notice here, right, I have a repeated index now. The sum is over that repeated index, okay, and the repeated index disappears. Keep wanting to skip the E. Index disappears. All right. So if you're struggling and it's normal, okay, to sort of be able to write this out, but sometimes to struggle to write it in the kind of general way like this. So if you're in doubt, write it out. All right. And then the last thing I'll say, sort of as the tip going forward for programming, is if you look up here, I said that we're going to think about loops. If you think back a couple lectures, we did cases where we did vector sums like this. All right, and every time we had a sum over an index, that's going to mean a loop, right? So think about that, right? We have this counter that's going through, and that's going to mean that we have a loop, all right? So in index, a free index, or I'll put it a different way. If I have a summation sign, with an index, okay, think loop. Okay, think needing loops. All right, so I've got, you know, one index, one dimension, so here I have two dimensions. I have a dot product, okay, that's going to give me a summation sign. Note that the repeated index is the one that disappears, okay, and if you're struggling with it, write it out. After a few times of doing it, you'll start to catch on. Okay, so let's just look at a quick example of this. I don't want to take too long, but let's just do a quick example. All right. So suppose I have. Let me give myself a new page here. So suppose I've got A is just this 2 by 2 matrix. I'm going to do A 0 0 A 0 1 A 1 0 A 1 1. Okay, I'm going to drop the comma because it kind of makes a mess. All right, x is equal to x0 x1. All right. Now, what happens when I do a dot x? Let's look at that. So a dot x is going to be equal to, let's do out our product. I'm going to have a0 0 multiplied by x0 plus a0 1 times x1. All right, that's the first one. Now I come down to the next one. I have a1 0 multiplied by x0 plus a11 times x1. All right, so now look at what happened here. Notice that these indices here obeyed the rules I talked about earlier. Notice I have the j here. I changed the j index, if I'm thinking about aij, right? The one, because I went over the two columns, multiplied by the rows there. So I can write that down as the sum over j of a0j xj, right? Because that one just went from 0, which was that one right there, to 1, which was the next one there. Okay, so this, you know, j goes from 0 up to 1. All right, and I can do the same thing down here, except instead of the 0, this first one right there is a 1. So this is a1, oops, not I, a1j and xj, again summing over j0 to 1. If you can read that, hopefully it's not too small. All right, so now I have a 1 in front, and I have that guy. So if I want to write that down in general for any 0 or 1, I can write that as a sum over j of aij xj. Okay, because I had the j's right there, and now I have this I, and that I can be either 0 or 1 is okay. All right, so notice that the I isn't repeated. Okay, so that means at the end of the day, this is going to give me some vector, right? Say yi, right? It's some new vector that I get out from that. All right, so that's just a little example stepping through that. So if I were going to write this in Python code, what would that look like? Let's think about that. So if I have y is equal to np.dot zeros of 2, okay, I'm going to need to make a y vector to hold stuff. And I'm going to start out here and have for I in range 2. Okay, that's this I loop that I'm going to need to store the yi. And then my inner loop is going to be for j in range 2. Okay, and that is this piece right here that I'm going to do my sum over j. All right, so I need two loops. Okay, I need a loop that's going to go over, you know, this one and this one. That's the j loop, right? I'm going to do j both in the same thing. That's going to be fine. Okay, but then I need another loop that's going to do this one and that one, right? So I need one loop to do the j's and then one loop to do the i's. All right, so that's right there. Okay, so now how am I going to solve this? I'm going to have y of bracket I is equal to a bracket I comma j multiplied by x j. And I made a mistake, so I'm going to go back and fix it right now. Okay, I need to make sure that this is a plus equals. So let me get that back. Plus equals aijxj. Because what happens is the first time I go through, I'm going to do a0, 0 times x0, and then I need to add to it a0, 1, x1, and that ends to the yi. The second time I go through this I loop now, I increments, and I do this on my first j loop, and I do the second one on my second j loop. All right? I talked through that kind of fast, right? But notice the similarities here between these formulas. Okay? I get yi, I have aij, xj, okay? So the formulas for index notation translate really well into what I'm going to code. All right, so we've done the loops. Hopefully you can look at this and reproduce how this gives each of these terms here. All right, and hopefully now you can look at the formula and see how that connects. And if you can understand this example, all right, you are well on your way to being able to just master this class. So if you don't understand this example, pause the video and go back and review. And make sure you understand every piece of how this is working and how they're connected together. Why, for instance, is it not right to have just equal sign? Why do I need a plus equals? If that confuses you, make sure you pause and go back and figure that out by looking at this formula and seeing how it plays in here and seeing how it comes in here. All right? So this example is really critical, and it's going to be very critical to understand this for our next lecture, okay, for next time. All right, that's it for index notation. Let's finish off our video with part 3, which is solving linear systems. All right. So how do you solve a linear system? I hope that you've already done this before. Okay, hopefully you've been doing this since high school, but we're going to review a systematic way of doing this called Gauss elimination. Okay, so how do, okay, there's many ways, right? But we are going to use what's called Gauss elimination. All right, and Gauss elimination is a way of doing it systematically. All right, so I'm going to write this. So systematic, okay, it's efficient. All right, so maybe the way you learn in high school, you have to do a lot of manipulations. Okay, this one, it's pretty efficient. You can do it the same way every time. Okay, so that's what I mean by systematic. So same way every time. All right, efficient, meaning you're not going to have to do that many steps. Okay, and it will be codable. All right, so we're going to be able to take this process and we're going to be able to turn it into code that we can do. All right, so let's think about an example. I think the best way to do this is with an example. All right, so here I have a dot x is equal to b, and my system, I'm going to use the system we've been playing with earlier. So 3 minus 1, 1. Minus 1, 2, minus 1. 1 minus 1 minus 1. Okay, multiplied by x0, x1, x2 should give me minus 3, 8, 1. All right, so what am I allowed to do to this? Recall that my rules say that I can, there are rules for manipulating matrices, say that I can multiply any row by a constant. Okay, that I can do. All right, and I can add rows together. That also is allowed. Okay, so if I can multiply by any constant, of course I could also subtract rows from each other because I could just multiply by minus 1. Right? So notice the rows, remember, rows are equations. Okay? So if I add a row together, it's like adding two equations. Okay? I can multiply any row by a constant because that's just like multiplying two sides of an equation by a constant, don't forget that I have to do the right-hand side also, right? So, don't forget the right-hand side as well. Okay, can't forget that one. All right, the same thing here. Don't forget to do the same thing to the right-hand side that you do the left-hand side, but as long as you do that, you're okay. Okay, so we're going to break this down into two steps. Okay, so in the Gauss elimination algorithm, okay, there's two steps. Step one is to make an upper triangular matrix. Okay, so what's an upper triangular matrix? An upper triangular matrix has, only non-zero terms above the diagonal. So where I'm putting the dots, those are non-zero, but there's zeros below them. Okay, so an upper triangular matrix will look like this. I'll get a system that looks like that. Okay, once I have an upper triangular matrix, in step 2, I can then solve for x2, okay, the bottom, all right, because now I only have, something times x2 is equal to something, okay, and I can just solve for that guy right away, okay. Then I solve for x1, okay, where I plug in x2 into the equation for x1. So now I have something times x1 plus something times x2 is equal to something. Well, now I know x2, so I can subtract that over to the right-hand side and solve that one, right? So, I'm going to have like x2 on for this guy, is like, something over something, right? Now here x1 is going to equal, something minus something times x2 divided by something, okay? And then I can keep doing this, all right, and solve all the way up to x0, okay, by having the same thing. So x0 is going to be something minus something times x2 minus something times x1 divided by whatever that coefficient was out there, all right? And I still plug in, x0, x2, and x1, working my way up. Okay, so these have names. This make an upper triangular matrix. This is called forward elimination. Right? I'm eliminating terms, getting zeros. This is called back substitution. Okay, as I work my way back up the x vector, okay, and I substitute in as I go along. All right, so let's do this. Let's do this for our example and do our practice here. Okay, so I'm going to need to copy down my matrix again. Where did I go? So I have 3 minus 1, 1, minus 1, 2, minus 1, 1, minus 1, minus 1. All right, and I'm going to actually, before I do that, I'm going to augment it, all right, with the term, this thing on the right-hand side over here. So minus 3, 8, 1. Minus 3, 8, 1. All right, so I write down my augmented matrix so that I don't forget to do the right-hand side. Okay, and the first thing I'm going to do is I'm going to start in this column. Okay, so I'm going to do column 0 first. So column 0 first. All right, and within column 0, I'm going to start on row 1. Okay, so column 0, row 1, that's what I'm going to do first. And I'm going to do the following. I'm going to take the ratio with the diagonal. Okay, so the ratio with the diagonal here is minus 1 divided by 3. Okay, so I take that ratio. I'm actually going to write it over here. Minus 1 over 3. Okay, I'm going to give myself a little more space here. All right, and what I'm going to do is I'm going to take row 1 minus 1/3 row 0. Okay, So I'm going to compare to the diagonal here, which is on row 0. I'm going to take that ratio right there, and then I'm going to take row 1, I'm going to take that whole row, and I'm going to work on doing minus 1/3 times row 0, so minus 1/3 times that row, adding it to that row, and I'm going to use that to replace row 1. Right? So hopefully I didn't bungle saying this, but what that should do is immediately you should see that I'm going to get a 0 here. And then the rest of the stuff, not guaranteed to be 0. What I'm trying to do is to start in column 0 and get a 0 in row 1. That's my goal. Okay? So let's write that down. So the first row doesn't change. In Gauss elimination, the first row never changes. Okay? If it's changing, you're doing something wrong. Okay? So what am I doing here? I do minus 1/3 times row 0. And so minus 1/3 times that one is going to give me a minus 1. It should be the exact same as this guy, right? Because when I subtract them, I want it to go away. So now I take row 1, minus 1, minus a minus 1/3, right? So maybe I should write that out. So I have minus 1 minus a negative, or minus a negative 1/3 times 3. Well, what does that equal? 3's cancel, minus minus comes a plus. That gives me 0. Okay, so I should have a 0 there. Perfect. I did that one right. Okay, then I have the next one. I'm going to have, let's see, 2 minus negative 1/3 multiplied by that guy right there, minus 1. So 2, let's see, that's going to be minus minus minus, so I will have a minus, and that's going to be minus 1/3. So I should end up with, that would be 6/3 minus 1/3 should give me 5/3. So I should have 5/3 right there. All right, then the next one I have minus 1 minus a negative 1/3 multiplied by a 1. Okay, now I have plus there, so I'm going to get minus 3/3 plus 1/3, and that should give me minus 2/3. So I have a minus 2/3 there. Okay, and now I do this last one, and I have an 8 minus minus 1/3 multiplied by a minus 3. So now that cancels, and I should get 8 minus 1, which should give me 7. All right, so now I have a 7 right there. Okay, so I did row 1. Boom, that one was done. Okay, so now I'm still on column 0. So I'm still on 0 here. Okay, and now I'm going to come and do, I'm going to come down here and do row 2. So I need to write it down. Let me write it down. I didn't change this one at all yet. Okay, 1 minus 1 minus 1, 1. So now I'm going to work on this one. Okay, and remember, I'm trying to do something systematic. So I'm going to do the same thing that I said before. I'm going to take the ratio with the diagonal. Okay, so take ratio with the diagonal. Okay, so that ratio is now 1/3. 1/3. Okay, and I'm going to do row 2 minus 1/3 times row, which row? 0. Okay, because I want to compare to that one right there, and I want to get rid of that guy. Okay, because I'm working on column 0 to get rid of that one. Okay, and I'm going to use that to replace row 2. Right? I'll do this one a little bit quicker. Hopefully it won't take up so much space here. So let me just copy this down. 3 minus 1, 1, minus 3 over here, 0, 5/3 minus 2/3, 7. Okay, now I'm ready to do this one. So 1 minus 1/3 times 3 should be a 0. Perfect, that's what I wanted. Okay, now I have minus 1 minus 1/3 times minus 1. So that means I'm going to get a plus 1/3. So this means I should have minus 2/3. Okay, then minus 1 minus a 1/3 times 1 should give me minus 4/3. And then 1 minus a minus, or minus 1/3 times negative 3, that gives me a plus 1, so this should give me a 2. Okay, hopefully I didn't lose anybody there. All right, and look at that. I have now successfully completed the column 0, right? So I said I'm going to start with column 0, and then I'm going to work my way through the rows. So column 0 is done. I now have no zeros left there. So now what I do next is I move on to column 1. Okay, so now I go to column 1. And where am I going to start in column 1? Am I going to start here? No, I'm not going to start here. I'm going to start now in row 2. Okay, because remember, I want to get an upper triangular matrix. So this is actually the last one I have to do. Okay, so now I start in row 2, and I do the same thing. I take the ratio. Okay, I said with. Now which row do I pick to do the ratio with? Okay, this is maybe the next tricky part. I don't pick this 0 row up here. I don't want to pick the 0 row, because if I pick the 0 row, when I do a subtraction, I'm going to fill that 0 back up, and that's a problem. So this is why I had to do column 0 all the way first. I needed to get rid of all those zeros so that I can subtract these two guys and get rid of this one. Okay, so I take the ratio with row 1. Okay, and so that ratio with row 1 is now minus 2/3 divided by 5/3. Okay, so 2/3, let me just write that down, minus 2/3 divided by 5/3 was going to give me minus 2/5. Okay, so now let's look at what happens when I do that. So I'm going to then take row 2 minus 2/5 multiplied by row 1, and use that to replace row 2. Okay, so let's check that out. So I'm going to have row 2, so I'm going to have minus 2/3 minus 2/5 multiplied by row 1, which is 5/3, and that should give me, let's see, 5 cancels. I have a minus 2/3, but that's plus, should give me 0. Okay, that checks out, so that one's going to be 0. So I can come write that down, give myself a little more space here. I have 3 minus 1, 1, 0, 5/3 minus 2/3. Over here I've got minus 3 and 7. Here's a 0, and I just found out I have a 0 there. Okay, so now the next one I'm going to have, giving myself a little more space, let me come down this way. I'm going to do this one. So I have minus 4/3 minus a negative 2/5 multiplied by, which one? That one up there, minus 2/3 is going to be equal to, and this one's a little bit harder, so I'm just going to cheat, okay, and tell us that this is minus 24/15. Okay, you can prove that to yourself. This should give you, 4/15 right here, and I guess this is 20/15, and I just did it. It's 24/15. Okay, so that's minus 24/15 right there, right? And then the last one is this 2. Don't forget that one. I have 2 minus negative 2/5 multiplied by this one right there, 7. Okay, so now I have the same issue here. So this is going to be 10/5. 10/5 plus 14/5 is going to give me 24/5. So this will be 24/5 right there. Okay, so that concludes. So this is the end of step 1. Right there. Okay, I have my upper triangular matrix. Okay, now to finish solving, or let me go back real quick and just review what we did to make sure we understand. Okay, so I started in column 0. I wanted all zeros below the diagonal. Okay, then I moved to column 1. And in each column, I went down the rows, and I started below the diagonal and did the rows. So I started column 0, went below the rows, started column 1, started below the diagonal, went down the rows. Okay, so what did I do? I start in column 0, okay, and then I looped over rows below the diagonal. Okay, I needed to make a ratio. The ratio was of the current row divided by the diagonal. Okay, divided by the guy that I cared about, right? So it was this piece divided by the piece on the diagonal. This guy divided by the diagonal. This guy divided by the one on the diagonal. Okay, that was how I made my ratio. Okay, then I multiplied my row by the ratio. Let's see, did I multiply the row by the ratio? I multiplied the row above with so not my row, it's the row of the diagonal. It's the row with diagonal by the ratio and added to current row. And then I replaced my row. Okay? And then I did that in column 0, and then I looped over my columns. Okay, like we talked about. All right, so hopefully that's kind of an exhaustive review of that. We're almost done with this. I'm belaboring it because we're going to code it next time, and I'm trying to get us to kind of beat it into our heads. All right, so if this seems a little bit monotonous, I'm sorry. Coding is a little bit difficult. Well, it's not difficult. I don't want to say that. It's a little bit detailed, so I want to make sure we get this down. All right, so how do we solve this now? Now we're going to loop our way back up. Okay, so this is the back substitution part. Okay, so now I have this equation right there. Minus 24 over 15 multiplied by x2. Remember, x2's are the ones that are in this column here, is going to equal 24 over 5. So now we can solve for x2, which is going to equal 24 over 5 divided by minus 24 over 15. Okay, and if I'm not mistaken, that gives us minus 3. So we've solved for x2. Hey, what's our next one? I don't want to lose my thing. I'll write it right here, and then we'll scroll down. I've got 5/3 times x1 minus 2/3 times x2 is equal to 7. Right? Let me scroll down here. Okay, so now I can rearrange and solve for x1. So x1 is equal to 7 plus 2/3 x2 divided by 5/3. Okay, so I can plug that in. I have 7 plus 2/3 times minus 3 divided by 5/3. And 2/3 times minus 3, that cancels. I get a minus 2 and I get 5 multiplied by 3 over 5. And that gives me 3. So x1 is equal to 3. So maybe I'll write that out here. x2 is equal to minus 3. Boom. x1 is equal to 3. Right? And let's scroll up one more time to look. Now I have my original equation. 3 minus 1, 1 minus 3. So 3x0 minus x1 plus x2 is equal to minus 3. So that's our last piece, and I can rearrange that one and solve for x0. So I have x0 is equal to minus 3 plus x1 minus x2 divided by 3. Well, I can plug those all in now because I have them here. So I have 3 plus x1 was equal to 3, and x2 was a minus 3, so I have a minus 3 divided by 3. Well, let's see, minus 3 and plus 3 cancel, and that's going to be a plus 3 divided by 3. That should equal 1. So x0 equals 1. Now I can write my x vector, which is 1, 3, minus 3. Okay? Whew, took a little while, right? But we did all the details, and hopefully you saw that. Okay? So how do we do this for step 2? Okay? So we start at the bottom, okay, and solve for x2. Okay, and then we work our way up. right? Work back to x0, okay? Substituting in. So subbing in for what we know. Okay, back substitution. Okay, so let me just close with just 2 or 3 quick comments. Okay, so there are easier ways, right? There are ways for any given system, right? There might be a trickier, easier way. Okay, easier if you have a special case. So maybe you can look at this system that I just did and you see some way to do it in fewer steps, all right? But, okay, but this way is systematic, okay? And it almost always works, okay? It always works unless there's a few cases where you have to like swap some rows around, all right? But it almost always works, okay? We'll talk about that a little bit, about when it doesn't work. Okay, so next time we're going to code this. Okay, so make sure you understand this as you go through by hand. All right, the last comment I'll say is you can always check your answer. So this is one of the great things about algebraic equations, and the next bit we're doing here with algebra is that you can always check your answer. So you can do aij times xj, right, summing over j, and you can check if that's equal to bi. So once you have x here, you can plug it back in and check, does that equal bi, right? And on your homework, you have to do this. You have to write a little code that'll help you practice a little bit of this stuff, okay, to show that you can check that answer. But then you can know that you're right. All right? So just to review, what did we do? So we started out talking a little perspective. We're switching from numerical computing to solving math problems. We introduced linear systems and a general notation for them, and we talked about index notation and how to convert between things you normally write by hand and vector notation and index notation, which is easily translatable to a computer. And then finally we ended up talking about how do we solve these systems using Gauss elimination, which is a systematic process whereby we do forward elimination step using these ratios and going over the columns and rows in a certain way. And then once we've done that, we have an upper triangular matrix where we have zeros below the diagonal. And then we substitute in starting at the bottom and work our way back up to the top and do back substitution. All right? So that's a review of matrix algebra. Best of luck on your homework, and we'll talk to you next time.